Hi everybody, we're going to talk a little bit about Diels-Alder reactions in this video. So a Diels-Alder reaction is a type of pericyclic reaction. So we've heard that word before when we talked about ozonolysis, how that was a pericyclic reaction. This is a very, very commonly used reaction in all of organic synthesis, really, because it does what it does very, very well and very predictably. So that's kind of a key. But what we're looking at with pericyclic reactions in particular is we're looking for a continuous ring of electrons in the transition state. So if we look at this reaction, what's happening here is we have a diene and we have a dienophile. Okay, so our diene and our dienophile, those two things are going to react together. We're going to have electrons moving in a circle. We're going to have arrows moving in a circle. So what we're going to have is we're going to see these two sigma bonds form. So we're going to have this to that to that. Okay, so if we look at what those arrows made, we made a cyclohexene. Okay, and I always think it's helpful to just kind of number these out. And I number them pretty consistently. I'll always have my diene be 1 through 4 and my dienophile 5 and 6. What you're looking for here is we are always going to be making cyclohexenes here. So the cyclohexane is really kind of our retron. It's kind of the thing that you look for in a molecule, and you see a cyclohexane, you go, I wonder if I could make that using a Diels-Alder reaction. So that is going to be the product that we're looking for when we're doing this for synthesis. So there's a couple of things that we want to consider here. Because this is what I drew up there is the most basic Diels-Alder reaction that you could have. It's actually one that's not really used much because the heat that I have here, it's actually quite high heat that you need in order to get this reaction to actually go. There are a lot of things that we can do to lower the reaction temperature that's required, and that involves changing things around with the regiochemistry. Okay, and remember when we're thinking about regiochemistry, we're thinking region. So that's where in the molecule is the reaction actually going to take place. So where are the bonds going to be formed? So what we'll often do is we often use an electron-rich diene with an electron-poor dienophile. Okay, so if you have some sort of electron donating group on your diene, that makes it electron rich. If you've got some sort of electron withdrawing group on your dienophile, it makes it electron poor. When you start to put kind of more polar things together, that's going to make a much easier reaction to accomplish. Okay, so that's one way to kind of affect the regiochemistry. We are going to find this by resonance. Okay, and you'll see what I mean in a second with that. Okay, the last thing that we need to consider is stereochemistry. Okay, so if we look at what we've done here, let me number these sleeves really activate this iPad. Okay, so if we look at 1, 4, 5, and 6, 1, 4, 5, and 6, they all started out as sp2 hybridized. So if they're starting out sp2 and then they're moving to sp3, that means that we have the potential to create 4 new stereocenters, okay, in one reaction. So we got to figure out what's going on there in terms of relative stereochemistry, okay? So for this, we're going to look for, so we need to determine it's completely illegible. We need to determine the relative stereochemistry or a potential 4 new stereocenters. Okay, because we got 4 new sp3 carbons there, so that's 4 new possible stereocenters. Okay, so to do this, we're going to use the drawing tool, which I will show you in a second. Or a 3D drawing. Okay, so I'm going to show you the drawing tool in this video. I'll show you both the drawing tool and the 3D drawing in class. Maybe make a video of the 3D drawing later. I've seen most students respond better to the drawing tool than the 3D drawing. I just show you the 3D one because that's actually how I was able to finally figure it out. When I was an undergrad, I did not understand Diels Alder, but when I went to grad school and I saw it taught to me using the 3D drawings, then it all clicked. So that's why I do that, just in case you need something else. But the drawing tool is also fantastic and super, and a lot faster than the 3D drawing, I will say. Okay, so we're gonna think about these 2 things. So let's just start with a reaction. Okay, and this is gonna be a lot more typical of what you would see for a Diels Alder reaction. They're usually never going to be as simple as the one that we started out talking about. Okay, and we're going to talk about, so we're going to use deuterium here. So remember, deuterium is just a heavy hydrogen. So that's just to kind of differentiate between this D and that H right there. And I just realized that I forgot one thing. The other thing with stereochemistry, since we are starting with sp2, we're starting with flat. We are going to be forming racemic mixtures. Okay, so the diene and the dienophile can either react like that or like that, and those are going to be enantiomers of each other. Okay, so now that that's done, we're actually going to keep going with this reaction. Okay, so we're going to react these 2 together, so our diene with our dienophile, using heat. Okay, and heat is really all you need for a Diels Alder reaction. There are some fancy Diels Alders that might use some kind of catalyst or something like that, but the simple ones that we're going to stay focused on, they just need the 2 reagents and heat. So you just heat it up and then you get your product out the other end. Catalysts can help you get single enantiomers. So if you've got a chiral catalyst, then you can do this to form a single enantiomer product, or just to help lower the reaction temperature. There's a lot of different ways to use them, but we're going to focus on just the non-catalytic versions. Okay, so the first thing that we always want to start with is the regiochemistry of the process. So we want the most electron-rich carbon to make a bond to the most electron-poor carbon. Okay, so to do that, we really need to draw some resonance structures. So for my diene, I'm going to look for something that has lone pairs on it, and that is going to tell me where on my diene do I have a buildup of negative charge. Okay, and we're specifically looking at these 2 carbons. Okay, if I end up with it on somewhere here, that actually doesn't help me because those 2 things aren't making any new bonds. So we're really just concerned about here. That's where we actually want to look. And in this case, there. That's the only place that we care about, because those two sets of carbons are actually going to be bonding together. So we're going to start off by drawing our resonance structures. We're going to start with the oxygen lone pair. That's going to push that pi bond over here. So let's draw that out. Okay, so then I get to this resonance structure. That's not one of the carbons that I'm actually caring about, so we're going to keep on going. Okay, so I can move the pi bond, move the lone pair into a pi bond, then that other pi bond into a lone pair. Okay, so now we can see what's going on here. If I'm looking at these two carbons, on this carbon, I ended up with a negative charge. Okay, so that means that if I go up here, this is delta negative. So that's where I want to have my delta positive connect to. All right, so now let's go ahead and move on to the dienophile. So in this one, I've got a positive charge right next to my dienophile. So that's kind of my electron withdrawing group, making that alkene electron poor. So we can see what happens when we use that. We'll put it over here towards that positive charge, which pushes the electrons over onto the oxygen. Okay, and I took electrons away from this carbon right here. So the dienophile, much shorter to draw the resonance structures of because there's only one pi bond that you need to worry about. So again, we're focused on these two carbons. It doesn't matter to me at all that I have a whole bunch of electron density over here. What matters to me is what the carbons themselves are actually charged. So that means I've got my delta plus up there. Okay, so if we see what's going on here, right now, I need to make those bonds. So because I'm kind of crisscrossed, actually I'm gonna do it with the green. So because I'm crisscrossed there, I just want to just rotate one or flip one so that I can have those two things not crossed over and straight lines. Okay, so I'm going to flip the dienophile. So my diene is going to stay in the exact same position, but I'm going to flip my dienophile so that I have the nitrogen. Oops, that's not nitrogen. So that I have the nitrogen up. Like that. Okay, so now I have my delta minus and my delta plus, and now I can have those two things go together, and I'm much happier here because now I've got them this instead of twisted. All right, so I need to make those bonds. So I'm going to do 1, 2, 3, 4, 5, 6. Okay, those are going to be helpful when we do this next part. Okay, so we're going to add the heat. Okay, so our drawing tool, I'm going to do it right over here. Okay, so the drawing tool, we're going to draw the diene above our dienophile. With our electron withdrawing group under the diene. Okay, and you'll see what that means in a second here. Okay, so I'm going to draw it fairly big. So I think it'll just be a little bit easier to see. Okay, so I always draw my diene first. And I always draw it kind of like opening up, like Pac-Man type style. And you'll get the Pac-Man even better in a second. So we want to draw our diene file under the diene. Okay, the way that we do that is we're going to make sure that we put the appropriate gaps in the lines so that it looks like you're sitting with one on top of the other. So we don't want to draw it over here. What we want is we want to draw it right in here, kind of snuggled up into the mouth of the Pac-Man. Okay, so what I want is I could have my NO2 over here, or I could have it over here. Okay, we want the electron withdrawing group, which is our nitro. So if it's withdrawing electron density in your resonance structures over here, that's your electron withdrawing group. We want it over here underneath the diene. Okay, and that looks like it should be really bad sterically, but keep in mind that these things are flat. And so there's nothing that's like poking up into it. They're flat going at it. So what's actually happening here is that there are orbitals that are interacting between these sp2 carbons and the nitro group there. And that's actually a beneficial orbital interaction. So it's actually perfect. It helps a lot in this reaction. So we don't want to have it over there. We want it under the diene. And then we need to make sure that all the rest of our dienophile is staying consistent with the stereochemistry that it started with. So our nitro group is on the same side as our ethyl. So that means our ethyl is going to be over here. Okay, so our ethyl group, and notice how I'm drawing the bonds with a little gap just to indicate that it is underneath the diene. And then we have an ethyl group on the other side. Okay. All right, I think I have everything on there. Oh no, oh, forgot my deuterium. That was close. There we go. Okay, so now I have everything drawn out. I'm sorry, this is just bothering me. There we go. Okay, so I've got it all drawn out. I've got my dienophile underneath my diene with my NO2 group under my diene specifically, under that kind of back side of it. So now I'm ready to think about drawing my product. I'm just going to add my numbers here. So the setup of the drawing tool is probably the hardest part. What we want to do next is we want to really show the Pac-Man. So we're going to just kind of extend the diene angle farther. Okay, by this time it should be very Pac-Man looking. All right, so if you don't have, you can use a highlighter for this or just kind of imagine it in your mind. But what we want to kind of think about here is that anything in here is inside. And then anything out here on the outside of the mouth is outside. Okay, so it's just denoted by these kind of imaginary lines here. So if it's inside the mouth, it's inside. If it's outside the mouth, it's outside. So anything that's inside is going to be cis to each other. Anything that's outside is going to be cis to each other. And the relationship between these two, inside and outside, will be trans to each other. Okay? All right. I want it right here, but then this circle is obnoxious. There we go. Okay, so we're going to draw this product. Okay, so I'm going to start off with my cyclohexene. I know that if I kind of think about, you know, there to there to there, I'm going to have my double bond right here. And let's go ahead and add some numbers here. Alrighty. Okay, it's so much easier if you've got numbers because it can be a little bit hard to see what's attached to where when you've got it drawn over top like this. So just keep that in mind, numbering, numbering, numbering. Okay, so we want to start off with anything that is outside is going to be cis to each other. So it doesn't matter which one you pick. I'm just going to go with a wedge for outside stuff. Okay, so anything that's outside is going to be on a wedge. All right, so on number 1, I've got the methoxy group. 2 and 3 don't have anything. 4 has my deuterium. So my methoxy is on the inside, on the outside. My deuterium is on the inside. So the deuterium has to be trans, okay, to my methoxy. On 5, I've got a methyl group that's also on the inside. And then on 5, I also have an ethyl group that's on the outside. And then 6, I have my nitro group, which is on the outside. So that needs to also be on a wedge. Like that, okay? So in terms of relative stereochemistry, that's what it's gonna look like. Obviously, we can get the enantiomer as well, like we talked about earlier, because I could either have my diene and my dienephal like this, or opposite, okay? It doesn't matter which side they're going on. We just tend to draw the drawing tool as consistently as possible so that you kind of get it ingrained in your head to do it a certain way, and then you follow your routine. Okay, so we're gonna practice this a lot, so don't worry too much about it, but it's gonna be good to kind of see it and think about it before we get started. So we will talk more about it in class, and have a good day, everybody, and let me know if you have any questions.